could be killer application type solutions. And so I saw that in ICC just a few weeks ago, he received the Stephen O'Rice Best Paper Award for his paper on ISAC. Some people call it RADCOM, you know, dual function radio and sensing, and radar and sensing, sorry, and communication. So, you know, he's got a little finger in so many things, really, all the way from the theoretical solutions down to practical solutions. And his title is, really says it all, it's meant to be. So over to you, Christos. Thank you so much for giving us the insight into your recent research.
Thanks a lot, Laios, for your, I'm hoping you can hear me. Yeah, so thanks a lot again, Laios, for your very kind introduction. And many thanks for inviting me to give this talk. I really appreciate the privilege to be able to talk to you about this technology that I really believe in. And I hope I'll convince you that it makes sense and it was meant to be, this integration of sensing and communications. In next generations of networks will be expected to carry out a number of services, not just next generation communications. Let me see if I can pick up my laser pointer for a minute, so I can show you around the slide. So not just next generation communications with its ever increasing KPIs, but services like localization through the cellular network, imaging and environment mapping, security monitoring, incident detection, perhaps moving away from this network of cameras, which can be quite personal and quite intrusive, support smart mobility and connected cars. And also there's this big push for intelligence native in the network. So gathering data, and what best way of gathering data than through sensing, right? And if you look at all these functionalities, they boil down to two main things. So communications, which is something we spent more than 5 decades developing in our wireless network, and also this new capability of sensing that is catching up. And to my observation, this area of sensing and communication started with the coexistence scenarios. So with the release of spectrum that's been traditionally occupied by radar for communications. And you have a number of scenarios for the coexistence of the low gigahertz bands, where typically the big radars used to live, like air traffic control. These are been parts already for 4G and LTE. But you also have the new radars, like the automotive radar, the smaller radars, the more ground down to earth radars, which occupy millimeter wave bands that are being looked at for communications within 5G and beyond. Now, this coexistence tends to be messy. You have this interference if you look at this very simple schematic of a communication downlink with a radar link, let's call it. So you get all this interference from the communication transmission to the radar echoes, from the radar transmission to the communication receivers. You need to do something about them. You need to coordinate somehow. You need to exchange information. And that can be risky. It can be messy. And you see this in the real world. So early last year, I think, in the US, we had planes being grounded of fears of 5G interference. And that's exactly this kind of coexistence. So the coexistence is quite risky when you have radar critical or communications critical applications like air traffic control, or communications when you're doing, let's say, a remote surgery and you want to have extreme reliability. And it's not just the coexistence though. I mean, there's other issues that need to be tackled. And one of them is the growing populations of sensors and emitters. And a classical example is that of the connected vehicle. So the connected vehicle, I think there was a discussion just now, the fact that the connected vehicle needs to connect to other vehicles. So vehicle to vehicle communications, vehicle to infrastructure, vehicle to grid even is one of the communication modes. And at the same time, for its navigation purposes, it needs to carry a host of sensors, cameras, LiDAR, but also different types of radars, such as long-range radar for cruise control or obstacle detection, medium-range radar, short-range for park assist, and so on. So you can see how, you know, all these sensors tend to add up, And we're living in an age where we're going through a silicon crisis. It's not easy to get the chips for all these. So it's becoming a non-sustainable problem. A similar trend has been observed. Let me see if I can push this a bit upwards. Yeah. A similar trend has been observed in the military domain for a number of years now, where shipborne or airborne platforms are required to do, a number of different communication modes. So friendly communications, enemy jamming, or in terms of radar, environment mapping, detecting threats and missiles and so on. And each of those tends to have its own platform, its own frequencies and so. And again, as you increase the requirements for performance, so does the size of the devices increase, so does the weight and volume and power of each of these devices increase. So there's been a drive for a while now. You can see a paper at the bottom of the slide of 2005, discussing whether somehow some of these capabilities can be merged, if not from the same platform, at least tightly synchronized or coordinated platforms. And ever since the development of wireless communications from the very early experiments of Guglielmo Marconi and the radar from Sir Robert Watson Watt for more than a century now, these two technologies have been developed in isolation, I would say. So very little in terms of interaction. I show here a fence here, perhaps exaggerating a little bit. But even though they've been borrowing ideas from one another, and I'll show some later on, they've been developed in isolation. So we always thought radar as a military thing, communications perhaps as a more commercial thing. There's some notable exceptions, such as the pulse interval modulation, already back in the 60s. And we now consider that as the first dual functional system that does both radar and communications. And that's from a radar perspective, trying to piggyback communication information. Nothing much for a long time, until about 2010, I would put it, when in terms of the coexistence, so moving on from cognitive radio now to coexistence between radar and communications, that's the time where I think we started thinking about the two systems together in some way and having to coordinate them somehow. And then since then, there have been a few sporadic, I would say, developments in terms of the dual functionality. So doing both things at the same time. Here is an example from the communication side. So an OFDM-based system that's trying to do sensing with the OFDM signaling. But again, quite sporadic and not much until quite recently. Nevertheless, the two systems have a number of commonalities that I'm sure you recognize. So there's beamforming, for example. So in terms of signal processing, there's beamforming in communications. You want to point your beams and minimize interference and obtain high gain links. For radar, you want to illuminate a target. So you want to beam signal power at a target. There's commonalities in theory and math. There's hypothesis testing involved in communications, in modulation detection, for example. Was this symbol transmitted or not? Was this symbol transmitted or not? That's a hypothesis test or a multiple hypothesis test. A similar hypothesis test happens in radar, where you want to detect whether or not a target is present at a range angle cell, for example. So a lot of commonalities in theory. There's estimation in both. There's channel estimation in communications. There's parameter estimation in the radar. I'm essentially doing the same thing. So measuring the channel somehow, and from that extracting information. And as I go into higher frequencies, millimeter wave, even the math becomes very similar. You have the geometric channels for communications that become very similar to the radar channels. And there's also duplication in hardware design. So you have phased arrays for radar for a long time, phased arrays for communications, and MIMO communications, and more recently MIMO radar. So duplication in hardware, duplication or commonalities in theory, in signal processing, and so on. And through these commonalities, I would put it in 2017, there's been an effort in integrating these two systems finally. I think it was meant to be. I hope I convinced you by now. And since then, we've had this development of the area of integrated sensing and communications. And I want to make clear that I think it's a step change from the coexistence. So in the coexistence, you have the two systems, separate systems, radar and communications, competing for the same resources, competing for power, competing for spectrum, who's going to shout louder and manage interference. Now you're moving to a paradigm where you have one device, one dual functional access point with a single transmission, with a single signal, a signal spectrum use, at the same time conveying information to communication users, while the same signal is useful to detect target, has these all these good qualities that allow it to detect a target at a distance. So instead of competing, you're now having systems that cooperate, and you can build mutual benefits for both functionalities. And I hope I'll be able to show you a couple of examples. And beyond that, if we think about the development of 5G, I think Harold put it nicely that we envisage having access points on lampposts or building walls and so. So these dense cell populations, this line of sight dominated wireless network, there's great opportunities once these cells become dual functional. So it's not just a communication access point, it's a small radar as well. Then we can have this opportunity to provide this pervasive sensing through the cellular infrastructure. And because all these things are connected, you have a backhaul, you have the opportunity to do coordinated sensing of an unprecedented scale. You have the opportunity to do, every time you transmit a communication signal, to extract some data from your environment and build intelligence, not just for your wireless network, but also for your smart city. So it's an unprecedented opportunity, I think, to build intelligence even. A bit about the gains. I think there are a couple of obvious ones. So the one obvious one is the hardware gain and the silicon gain and the power gain, where before you had two separate devices competing. Now you have this one, let's call it super dual functional access point that does both jobs, right? So you're saving in chips, in silicon, in power, and so on. You have the spectrum gain, where before you had separate spectra for radar, separate for communications, and these guys had to live with all kinds of other applications that demand the spectrum. Now you have one bit of spectrum that can be used for both, and that makes space for all the other things that want to use the same spectrum. A couple of non-obvious ones is once you now co-design the two systems from a single device, cooperating, you have the capability to design scalable trade-offs between sensing and communications. You can go all the way from radar priority to radar critical applications like air traffic control or a smart traffic scenario, all the way to communications priority for communications critical applications like the remote surgery I mentioned earlier, and many others, and all the way in between. And I'll show you some examples of these very scalable trade-offs. And beyond trading off performance, you can actually create synergies between the two, where the sensing functionality can assist the bottom line communications performance, or the communication functionality can assist coordinated sensing and so on. And synergies with other important functions of the network, like security, that I hope I'll have the time to discuss briefly. In terms of use cases, at least from an academic point of view, a naive academic point of view, these are things I can see happening. So in the cellular network, I'm guessing the letters are a bit too small, so I'll take you through some of them. So sensing can be used for channel estimation, channel knowledge, build ray tracing models. Sensing can be used for crowd sensing, for localization, human detection, human counting, and all these passive sensing, cooperative localization, and many other applications through your cellular network, through this dual functionality. There's many applications in the vehicle network, such as vehicle-to-everything communications, and also at the same time obstacle detection. So these two functionalities are very important in a vehicle scenario. There's opportunities to improve efficiency through carpooling, reducing distances between cars accelerating together, and so on. And everything that can be done for cars can also be done for drones. And that's a more virgin territory in terms of standardization, maybe, and opportunity. There's opportunities for remote sensing and communications through high altitude platforms, satellites, or high altitude drones. We have these technologies already. We have satellites monitoring weather or monitoring the earth, monitoring pollution, and so on, and separate devices doing your satellite communications. So why not join these together and improve your efficiency? There's use cases in the smart home from presence detection, proximity detection, gesture recognition and interaction with the environment, detecting falls. For some communities, this is very important. Monitoring your sleep, monitoring your vital signs, your breath, your breathing, detecting intruders. All these are radar applications. Why not have these done through your Wi-Fi or a one device that does both communications and these sensing applications? And if you want to compare it to cameras, which you could install in your home, I guess one gain is the through-wall penetration of radar. I think Harold also mentioned this part of his optical bit. Unlike optical, let's say, systems, the radar can penetrate through walls. And that's another application where you can do better than a camera, let's say. And there's other applications. Maybe I don't want to spend too much time, but gesture recognitions, maybe some of you are familiar with Soli, where you want to use gestures instead of touching things or using mouse or whatever, especially in the COVID area where we don't want to touch things. There's applications as in augmented reality. Augmented reality relies on high data rates, so that you have all this projection of this virtual reality, and gesture recognition and radar in terms of interacting with this augmented reality. There's applications in medical health, again, relying on radar principles to detect things in your body, and also communications to convey these. And also, these smart devices and smart watches, why not, get rid of those and do them through your Wi-Fi or whatever, non-intrusive device. There's applications in digital twins. So when you take a physical device and you transform it in the digital domain, that involves sensing, mapping the device, and also high-speed communications. And similarly, in Industry 4.0, where again, you want this human to machine interaction, and that also relies on both functionalities of sensing and high reliability communication. And because of these potential markets, there's a lot of industry buy-in. There's a few names here mentioned, where industries are looking at millimeter wave joint communication and sensing. Sensing is being part of the roadmap, or sensing as a service is being recognized as a market. And also this example of Huawei has been a strong proponent of harmonized sensing and communications for a while. And there's now activities in the standards. There's quite a few here, but I would pick out perhaps the IEEE 802.11 activities. That was probably the first to pick up sensing through the wireless LAN. And more recently in 3GPP, there's these groups that are basically at the moment, as far as I understand, study groups. So feasibility studies on sensing through the cellular infrastructure, cooperative communication and sensing. What else is here? Sensing beam, transmission beams, and a few other discussion points. And all this ecosystem, I think the way at least I perceive it, as you've had from 1G to 5G, all these step changes in technology, sensing is going to be a first step between 5G and 6G. And I see sensing, because it's so broad and this integration of communications, I see it as a first generation of integrated sensing communication systems, which I see developing further as technologies advance, as the market grows, in a second generation and a third generation of such integrated sensing communications network. And this is the evolution. I think I probably covered this, but it all started from spectral coexistence, moving on to co-located hardware, where you have separate hardware, but closely located, so the coordination becomes easier. And the next step has been this joint signaling and joint processing, which allows you to do things through one device, both functionalities. And as I said, I guess the ultimate aim is to have this pervasive network, at least for 6G and beyond, for the cellular network, to have this pervasive network that every access point can also act as a small radar. And that's where you have, the truly unprecedented scale of sensing. In terms of research, wireless communications is quite mature in terms of theory development, signal processing, RF and hardware design. So is radar. And I hope I can use this talk to convince you that there's many open problems and many things for you guys to join in the research. There's very little in theory. We've already started a few groups around the world. Signal processing is a bit more advanced, but many things to do still. And hardware and RF design solving these problems of doing both things, radar and communications from a single device. All these things need to be developed. And there's very little at the moment. We're at the start of this era, I think. Plenty of space for people to do research on. Now, let me focus a bit on the signaling, which is what my team works on. So DFRC technologies, so dual functional radar and communication technologies, in terms of signaling, can be split into three categories. One is what we call the radar-centric design, and the principle is shown here. You take a radar waveform, you somehow modulate that waveform so that it conveys information, and then suddenly you have a dual functional waveform. And there's many ways of doing it. This pulse interval modulation is the very first one back in the 60s that I mentioned, where the position of the pulse in time conveys information. It's used as an index. There's more generalized index modulation systems working on the antennas, on the frequency, on the bandwidth. I'll show you an example from our lab. And there's also opportunities to do side lobe signaling. So use your main lobe for radar and use your side lobes for communication users, and many other more recent technologies. There's what we call the comms-centric design, and the main principle is shown here. You take a communication waveform, you use that waveform as your probing signal or your reference signal to do your radar processing, and then suddenly you have this dual capability. So you're transmitting your comms information, but using that signal to do sensing. What are the pros and cons for each of those? For the radar-centric, so both of them are quite compatible to the existing systems. So the radar-centric, it's quite easy to take a radar. We've done this in our lab, a working radar, modulate somehow information on that radar, and suddenly you have the system. So it's quite compatible, quite easy to apply this to a radar system. What's the problem? Radar waveforms are not designed for communications, so the data rates or the communication performance you can achieve is relatively limited. You're limited in the amount of bits you can piggyback on a radar waveform. Similar for comms. So a comms or centric approach, it's going to be very close to the standards. You can take an OFDM frame and somehow use parts of it for sensing or allocate resources for sensing. But again, you're quite limited in what you can achieve in terms of sensing performance, and you're quite limited how you can tune the sensing performance. So if I want to do more in terms of sensing, usually the penalties are quite significant. And that's where this third category of schemes comes in, the jointly designed schemes, where you design a signal from the start. And that's where you can actually get really these scalable trade-offs that I hope I'll convince you in the next few slides. So here's an example of this joint design. So if we look at an elementary scenario, this dual base station that wants with a signal to transmit communication signals to users and with the same signal to detect a target. A rather elementary way to design this is through a weighted optimization. So if you look closely, perhaps I won't go into the math, but those of you who are familiar with MIMO, you see here if X is the signal I want to design, what comes out of these antennas, H is the communication channel, and S is the information I want to convey. Anything that lives inside here that's not S is multi-user information. So that's a typical communications metric. So I'm here minimizing this the norm square of that multi-user interference. And at the same time, this is my radar metric. If X0 is an ideal radar waveform, there's many ways to design a radar waveform. What I'm doing here is I'm maximizing the proximity of what I actually transmit, the dual waveform, to an ideal radar waveform. So my communication metric, my radar metric. And you can have all kinds of constraints. We have a very elementary total power constraint, which is important for a downlink. But you can have more hardware-friendly constraints like constant modulus constraints to take care of your power amplifiers, or peak to average power ratio constraints, and many others. And the key thing here is this weighting factor, rho, that goes between 0 and 1. When rho is small, close to 0, this guy goes away, and I'm focusing on radar. When rho goes to 1, this guy goes away, and I'm focusing on communications. And tuning rho between 0 and 1 gives you this flexible, graceful trade-off between radar priority, communications priority. So that means you can go all the way from full radar performance, 100% radar performance, your radar reliability, reliable sensing, all the way to full communication performance, your high data rates, and anywhere in between. And here's a characteristic example where we have the radar probability of detection against the communications achievable rate, bits per hertz per user here. And let's take this plot, and you can see here I prioritize my radar, and I get a very good radar detection probability, all the way to prioritizing my communications, where I get my maximum communication rate. And I want to point out two things. So first is, even when I put all my priority on radar, I get some sort of communication rate, a non-negligible communication rate. Even when I put all my priority on comms, I get something better than a random guess, something better than 0.5. And I can move all the way along this curve, which is something I cannot do with coexistence. I cannot do very flexibly with radar-centric or comm-centric approaches. And this trade-off becomes more and more benign as I increase my degrees of freedom, the ratio of antennas to users and targets. And you can see here, when I increase this ratio, I can achieve my maximum rate with a much smaller sacrifice in terms of radar performance, and vice versa. And just to convince ourselves that this is not just theory, we've tried this in our lab. This is the communications lab in UCL. And we use this array of 6 antennas to emulate a dual functional access point. We have these 2 users, 1 antenna each. And for the radar, we assume there's a direction we want to scan, and we'd like to form a beam towards that direction. And we'll measure the quality of that beam with this antenna over here. And this is the kind of measurement we typically get. And we've observed this trade-off over the air with this tunable weighted optimization, where you go all the way from communications priority, a nice clean QPSK constellation, but very little in terms of beam pattern, all the way to a nice clean beam pattern for radar, but very little in terms of communications, a very blurry constellation. You're going to need to work on your constellation to resolve it. But also anywhere in between. So for example, 0.5 equal priority. You have a blurry QPSK, which you can probably equalize, and a noticeable beam pattern. So I hope it's clear that you can trade off these two things, and we've observed this over the air. And we've done an elementary activity detection with the same system, a people's counter, let's call it, trying to detect somebody crossing our beam, and we emulate that with this material here. And with simple power detection, we've been able to plot probability of detection and probability of false alarm, somebody crossing our beam. And through this decision gap here, you can guarantee that you can pick thresholds where you have a very good probability of detection, a very good probability, very low probability of false alarm. And you can find the details in our paper here. We've also tried the radar-centric approach in our radar lab. So this is a snapshot of our radar lab, where we have a radar transmitter, a radar receiver, an emulated target, and a communication receiver. You see here our radar lab works with very discrete antennas, but you have to do that in indoor scenarios, very directive antennas. And we have an FPGA-based platform system on RF system on chip platform, where our radar team are able to generate flexible waveforms, flexible bandwidths, flexible carrier frequencies, and a selection of radar waveforms. We picked a linear frequency modulated waveform, and we used 3 indices to convey information in the index modulation style. We use the center frequency of this waveform, its bandwidth, and the polarization of our antennas. So changing these indices conveys bits. And with these numbers over here, we've been able to construct a constellation of 10 bits per symbol. So every time we transmit a radar pulse, we also convey 10 bits of information. And we've been able to observe a trade-off by changing the duration of this pulse. So communications wants a short pulse, so you have more of these per second, so you have more bits per second. Radar wants a long pulse, so you can enjoy a good integration gain over the pulse. So by tuning this pulse duration, you get this flexible trade-off. And here's the throughput performance with increasing SNR, so the communications performance. And as we reduce the duration of the pulse, we can reach, a few megabits per second. And you can see how this, because it's index modulation, you're quite limited in terms of what you can achieve in terms of data rates. If you want to push forward, you need to sacrifice a bit more. And the actual trade-off is shown here. So you have the radar SNR against this maximum throughput, these values over here. And you see how when you push for higher throughput, you sacrifice some of your radar SNR, and vice versa. When you prioritize radar, you sacrifice some of your throughput. And a similar trend with the Kramer-Rao lower bound, so your estimation accuracy. Now, in the time I have left, I'd like to, given this is VTC, I'd like to give a vehicular network example where I'd like to talk about these synergies that I spoke about. So an example where sensing and direction finding of radar can assist communications. So how does beam training happen in a communications only system? It typically relies on transmitting a beam from the roadside unit, the user receiving that beam, estimating something about that beam, either the full channel estimation or the quality or the SNR can achieve, and feeding back that information to the roadside unit. So quantizing that information, feeding back either CSI or feeding back its preferred beam index as a minimum. And then once you want to refine the beam, you need to iterate this process. And you can see how this eats up my data block. It's overheads that I need to pay. So if this is your data, your frame, this is what you need to address for beam training. This is what you got left for data, right? So as you want to refine your beams, you're eating up more of your data block. Now, the opportunity we have with ISAC, so this is an application of this signaling that I was talking about. Once you have a roadside unit that is dual functional, it means every time it transmits a data block, it can use the whole data block and the echoes from the car, from the communication user, to do radar. So radar means estimating the direction of the car. And with simple prediction, I'll show you an example of Kalman filtering. You can predict where I need to beam next. So you see how the angle finding of radar can be used for beam pointing for communications to assist the bottom line communication performance. And the advantages here is there's no feedback. So you can use the whole block for sensing all the time, and you can achieve a better match filtering gain for radar and for sensing. Because there's no feedback, there's no quantization errors. You avoid errors in reception of that signal, of the feedback signal, and so on. Without going into the math, this is how it works. You can build a state transition model that carries all the radar parameters you need: angle, distance, velocity, cross-section, and so on. With basic radar measurement, you can extract the angle, which is what we're interested in here, and you feed that angle into your beamforming. And you know where you want to beam next using this straight state transition model and simple extended Kalman filtering. And here's a snapshot of performance. We're comparing 3 techniques here, 2 communications only techniques that I won't have time to discuss in detail. And the blue line is the ISAC based technique. You can see that one of the techniques breaks down. The scenario is, I forgot to say, you have a vehicle moving along the direction of a roadside unit. So you can imagine as the vehicle comes closer, the angle changes much faster, right? And the communications, because of all this feedback mechanism, they lose track of the angle. You have this misalignment of angle. But for the sensing-based approach, because you can use the radar and track all the time, no problem, the angle, you get these increasing data rates. The increase is because of the reducing path loss here as you get closer to the roadside unit. And another thing I'd like to discuss, which I think is important and unique for ISAC systems, is security. So if we look at, again, our elementary example, the dual functional system, now you're transmitting your probing signal for radar is the same signal for communications. That means your probing signal carries information bits that are useful to your communication users. What does that mean? You're opening up the opportunity to the target to act as an eavesdropper and extract this information. And there are scenarios where perhaps this is not a problem, but there are scenarios where, this is a real problem. And you can tell me I can encrypt, the data bits with higher layer encryption, so the target won't be able to extract them. But in some scenarios, just detecting that there's a link on the ground is critical information. I guess there's clear military scenarios where you don't want that to happen, but also in the smart city era, there's going to be scenarios where you don't want even the existence of a link being intercepted by anybody. And that's where I think physical air security comes in. And thankfully, we have a few decades of physical air security development. But what I think what the uniqueness is in this scenario, this lies in the radar link, if I can call it that. So if you think about the radar link, on one hand, you need to beam a lot of signal power towards the target to illuminate it. But if the target is acting as an eavesdropper, you want to limit the amount of power it can use to eavesdrop your information, right? So these are conflicting aims. On one hand, you want to beam a lot of power. On the other hand, you want to limit the amount of power that can be used for eavesdropping. And at the same time, you want to also provide good quality of service to your users. And this conflicting objectives means you cannot use techniques like null steering. You cannot steer a null towards the target. You want to illuminate the target. But you can use other techniques like artificial noise and jamming. And here's an example, another trade-off. We've used an artificial noise design. And we've shown that in this scenario, you can trade off secrecy rate, so communications, secure communications performance, against the peak to side lobe ratio for radar. So you push the peak to side lobe ratio for radar priority, sacrificing some of your communication security, and vice versa. If communication security is your priority, you can gracefully sacrifice your radar performance. And another technique that I think is very suitable is exploiting interference, this constructive and destructive interference. And this is an area that together with Laios as well, part of my Royal Academy fellowship, we've been working on for more than 10 years. And how it works is looking at the modulation level, the constellation level. Anything that pushes my signal away from the decision threshold is constructive. Anything that pushes me towards the decision threshold is destructive. And you can scale this to higher order constellations, and yes, also QAM constellations and so on. And we've applied this in communication-only systems for a long time, and we've seen orders of magnitude gains compared to classical approaches, the red lines here. You can decrease the power by 10 dB, I think we show in this figure, for getting the same symbol error rate. Now, how does this apply? So very briefly, what the main principle is, if I take QPSK, these green shaded areas are my constructive regions. If I equalize the phase of all these constellation points, they all fold onto the real part of the, on the real axis. And all these green areas fold onto this area. And then with simple geometry, you could derive criterion such that your received signal falls inside the constructive region. And this is the math here. And you can see here this real and imaginary part of my phase rotated received signal. And gamma, importantly, gamma is an SNR parameter. And that means you can go to classical optimizations with classical SNR constraints and replace those with constructive interference constraints. So how do we apply this in this eavesdropping scenario? So in this case, we want our communication users to benefit from constructive interference. So all these guys, we want their signals to fall onto the constructive region of the constellation. You want the eavesdropper, the target acting as an eavesdropper, not being able to detect the signal. So in this case, you want their signal to fall outside the constructive region where the detection will fail. It will get it wrong, what signal was transmitted. And you can use this, again, not going into the math, we're maximizing the radar performance here, subject to constructive interference constraints to the users, destructive interference constraints to the target acting as an eavesdropper. And this is how it works. Perhaps I'll only focus on this figure. If the green dot is what I'm transmitting, 1 plus j, if I think of QPSK, the blue dots are what the communication user receives, always constructive, always on the right direction, so a good symbol error rate. The red dots is what the radar receives, acting as an eavesdropper. And you can see they're all around the place. So the radar basically does a random guess of what was transmitted. That's the case where I only exploit constructive interference, QPSK and 8PSK. When I do destructive interference to the radar, to the target, you can see that the target always receives a signal that's outside the correct constellation region. So it would always get it wrong, the signal. And you can see this, here we measure security with symbol error rates. So the users, you can see the benefit from a declining symbol error rate as we increase the SNR, while the target, this is a constructive case, it has a constant symbol error rate of 0.75. This is QPSK. So this means in this case, 3 out of 4 times the target gets it wrong. And you can push this symbol error rate towards 1 if you employ destructive interference. So that's another useful tool that we can exploit to provide security in this sense. And the final thing I want to talk about is, I think it's an entirely new thing. I'm not aware of any work, even in the radar domain, doing much on this. So if you imagine in, let's say, 10 years from now, or whatever many years from now, you have this infrastructure that is designed for both sensing and communications, and you have, your users enjoying sensing services and mapping the environment with these new signals, these new dual access points and radars. You're opening up now the opportunity to unauthorized users to do the same, to map the environment, exploiting these signals as signals of opportunity. And that's an entirely new vulnerability for the wireless network. We've never had anything like this. It's beyond data security, it's sensing security. So you're risking of having sensed informations being leaked. And it's not a data link that you can encrypt. There's nothing to encrypt here. It's information about the environment that you're opening the opportunity to this malicious guy over here, the UAV, using the signals of the network to extract its own information. So you cannot do higher layer encryption. You need to do physical layer stuff. And we've made the first attempt on this. It's difficult because we don't know what metrics to use. We cannot use secrecy rate. That applies to data. You don't have secrecy rate for radar, but you do have mutual information for radar. There's quite recent studies on mutual information. It's basically a metric of how much you can estimate from a target based on the radar channel, let's say. So we've used the mutual information gap. So in this scenario, we have a dual functional transmitter, a legitimate radar receiver, an illegitimate radar receiver, our eavesdropper, and communication users. And we're using the mutual information gap between the legitimate user. You want your legitimate user to be able to extract a lot of information. You want the eavesdropper to extract minimal information. And you can maximize this gap in mutual information. And once you do that, this is the trend you get. Another trade-off. So mutual information gap. So now our sensing security metric against the communication performance of these guys. And you can see a graceful trade-off always. The blue line is the baseline where you don't do anything about the eavesdropper. You just maximize your legitimate receivers, mutual information. The red line is where you do this kind of optimization. And the orange line is when you augment things with artificial noise. So you get this extra performance. And you can see always a graceful trade-off between sensing security this time and communications performance. With that, I think I'm close to the end. Sorry if I took a little bit more time. I just want to leave you with a bit of a vision of what I think needs to be done. There's definitely more in terms of waveform and signaling design and making these more hardware efficient and reducing complexity. A lot of what you saw here is based on optimization, and you want to be able to reduce that complexity. There's a lot to be done in terms of these synergies, sensing assisted communications, communications assisted sensing. I showed you some elementary example, a vehicle going in a straight line. What happens if I have a curved line? What happens if I have many vehicles? So many problems that need to be dealt with. There's definitely a lot in terms of security. I hope I convinced you these are new vulnerabilities that we need to take care of. And if we think about these being deployed in dense cells in a smart city environment, there's going to be multiple cells living in the same spectrum. So you need to come up with multi-cell technologies tailored for dual functional systems. So bridging the gap between multi-cell communications and multi-static sensing. And finally, a bit of advertisement. If you're interested in this area and you want to start off, I hope I convinced many of you this is a worthwhile area. We have this book that's already available online and is coming up in hard copy as well, which has a wide coverage of ISAC topics. And with that, I definitely want to thank the team, the members of my team who've worked in these areas and acknowledge the funding. And I'll leave it at that. I'd be happy to discuss any questions you may have.
Thank you so much. Wow. What a journey this has been. Thank you again. Talking across the barbed wire and then eventually joint optimization, moving in the Pareto optimization direction, right? So theory and practice and so on. So over to you just for a few more questions. Obviously don't want to cut too much into the coffee break. Again, Jae-Hong.
Thank you for your comprehensive presentation on this interesting subject. I think the direct sequence type spread spectrum might be a good solution for the joint communication and ranging. The DS spread spectrum has been used for the radar for its the high resolution ranging and the anti-interference capability, and also the DS spread spectrum has been used for the wireless communication for its anti-interference capability and the multiple access capability. So those two could be combined very easily together, and then most of the discussion you gave today can be applied to that, including the MIMO and the phase array and then security or something. I would like to hear your view on that. Yeah.
I absolutely fully agree. So the direct sequences, direct sequence spread spectrums, these pseudo noise sequences are known for their good autocorrelation properties, which are important for sensing and radar. They've been widely used for CDMA, for communications. They are very good candidates. As far as I understand, I think some of them are used for optical links as well. So definitely very good candidates, good security performances. They hide inside the noise, right? So you get this covertness for the secure sensing that you need. Absolutely, great candidates for this kind of technology. Yes.
Yeah, thanks for that mini keynote, Jae-Hong. That's really great. And of course, we have such a rich literature on the subject of multi-carrier CDMA and all the associated aspects. So one more quick question, perhaps.
Thank you, Christos. Paul Ferver again from Catapult. I'm very much a fan of these multifunctional systems, and today I'll be talking a little bit later about joint communications and navigation systems using low Earth orbit satellites. One of the things that we've identified were two things actually. First of all, that there's opportunities for optimizing the waveform, so it actually carries a sequence which is good for both ranging and Doppler. And the other consideration is from a geometric perspective, the multistatic. You mentioned this consideration, and if we're talking about in the future a pervasive network, multiple sites. What do you think the challenges are going to be for things like joint estimation and using the signals from multiple towers simultaneously to improve information?
Okay. So on your second point, which I remember a bit more, so the multistatic, I think it's going to have to happen because there's limitations. If you think about it, you know, an ISAC device needs to be transmitting signals for communications and at the same time listening, right, for radar echoes. So you either have to have a full duplex technology, and talking to the full duplex guys, this is clearly an opportunity for them. They see this, they see a match now, they found their key application to develop full duplex, but that's going to be challenging in many scenarios. So you're going to need this multistatic approach. So one base station in uplink, also listening for radar echoes, while the other base station, the downlink base station, transmits these dual signals. That's definitely going to be, I think, a scenario. And you have the opportunities to, I mean, multistatic will give you all these different angles of view. So the mapping will become much better. As you go higher in frequencies, you're going to increase resolution. There's plenty of opportunities. And once you have this network of radars that are tightly coupled, right, with all these backhaul connections, you have the opportunity to do, you know, unprecedented sensing. And I forgot the first, the waveforms. Yeah. So I don't think we've answered this question in this work. We keep calling them waveform design, but it's the signaling design, the precoders, the transmit signal. In fact, in our lab, even the joint design where we say we design new signals, you know, we implemented it on an OFDM frame. So I don't think we've answered the waveform design yet. It's going to be a difficult, I think, adventure to go away from OFDM because OFDM is part of the standards. I think we're gonna have it around. There's definitely candidates like OTFS, but I think They still need to prove their worth and their practicality. But yeah, I'm looking forward to seeing what happens in this space.
We would definitely love to have you in the panel discussion because you have a treasure trove of really intriguing questions. But yeah, join me in thanking Christos again for this wonderful talk. And just really